All right, so we start today by kind of taking those last two concepts that we look at, those being of pressure and temperature, and relating a third concept, the third concept being the volume. And we're going to start talking about some of the relationships that gases have in terms of those three parameters. And what's interesting to note about gases in particular is that because gases are kind of unique in the sense that gases always fill their containers, gases are spread far apart from each other. Because of those things, they tend to have more unique properties, and we're going to kind of situate them accordingly. Michael, question? I'm sorry? So in particular, we are going to look at three different relationships. We're going to look at the relationship between the pressure of a gas and its volume. We're going to look at the relationship between the volume of a gas and its temperature. We're going to look at the relationship between the temperature of a gas and the pressure of that gas. And so what this brings us to are what we call the gas laws. And the gas laws are situated in this kind of way to tell us what the relationships are qualitatively, just based on observation, and quantitatively in terms of mathematical descriptions. And so the first law that we're going to explore is Boyle's law. Boyle's law is named after Robert Boyle, the British physicist who did some gas phase work looking at fixed temperatures. So what he noticed is that if you hold temperature constant, pressure and volume have a very set relationship. And that set relationship is an inverse relationship. If I decrease the volume of a gas, the pressure inside of that container increases. And if I expand a container, the pressure inside of the container decreases. They are inversely related. And if you think about it, you can kind of reason your way through that. Ever blow up a balloon and then you push it on the sides of the balloon? What happens is that as you're pushing in on the sides of that balloon and trying to make the balloon smaller, the gas inside starts pushing back at you. It becomes harder and harder to actually compress it. The more you push on it, the more it pushes back. That's Boyle's law in action. Now, mathematically speaking, we would call this relationship an inverse relationship because the two parameters are affected in opposite directions. And when we have an inverse relationship, that means that we are going to multiply the factors. So mathematically speaking, if I have an inverse relationship, I can get equality by multiplying the factors and comparing them. So these little ones and twos indicate a set of conditions. The pressure times the volume at the first condition, let's say like right now, is going to be equal to the pressure times the volume at a new set of conditions. And so from that perspective, if I double the pressure, the volume goes down by a half. 1 times 1 is 1. 2 times 1/2 is also 1. So whatever happens on one side, the opposite happens on the other. That's Boyle's law. Again, an inverse relationship. Our second gas law is attributed to Jacques Charles, a French physicist, and his relationship regards temperature and volume. So things to know about this one: the pressure is constant in these situations. We're only looking at changes in temperature and changes in volume. And the relationship here is direct. Which means that instead of multiplying the factors together, we're going to divide them by each other. Now, temperature and volume, that is a direct relationship. Easy experiment to do at home. Again, think about a balloon. If I blow up a balloon and tie it off, if I then take that balloon and put it on a bowl full of ice, the temperature of the gas inside the balloon is going to go down, and the balloon is going to shrink as a result of that temperature change. Pressure is going to be held relatively constant because the pressure inside the balloon and the pressure at the outside of the balloon is probably going to be pretty close to even. But the temperature is going to make the massive change based upon that. If I take that same balloon and instead of putting it in a bowl of ice, I put it on top of a bowl or a pot of boiling water, we'll see that the balloon will expand. And depending upon how hot it is, how big the balloon is, it can expand almost infinitely, or at least within reason, or it expands too much and the balloon pops as a result of just being stretched out too thin. But for direct relationships like these, the factors that we are going to use are going to be divided by each other. So my volume goes up, temperature goes up by the same token, by the same margin. My volume goes down, my temperature goes down by the same margin as well. Relatively straightforward. One important wrinkle here: these temperatures have to be absolute temperatures. So the temperature must be in Kelvin. One of the reasons why we are teaching you about Kelvin is this. Calculations are regarding energy, regarding movement of particles, regarding temperature kinds of studies where we're looking at proportionalities, require Kelvin measurement. Because otherwise, we could run into some real significant problems here. If I use Celsius, well, if I put a negative value in for T1, that means that potentially I have a negative volume, which doesn't make any sense. And let's not even get started on if one of those temperatures is 0. Then your calculator starts freaking out. So we have to be in Kelvin temperatures, because Kelvin temperatures will always be positive and they will never be 0. We're not going to have any concerns at all for gases at 0 Kelvin. That's absolute 0. It's a unimportant point to us. All right, so that's the second gas law. There's one more. Gay-Lussac's law, named after Joseph Gay-Lussac. If you've got really good French, I think the actual French pronunciation is something like Gay-Lussac. It doesn't really matter. I do not. If I can pretend by trying to sound really smart when I say French names. So we've talked about the other two parameters kind of balanced against each other: pressure, volume, volume, temperature. The only combination that's missing is pressure temperature. And once again, we can see two things. First of all, this has to be done at a constant volume. And second, we can see that this is a direct relationship, because we can see that the factors are being divided. Now, the best analog to this, because it's hard to keep a gas at a constant volume. Most things that we can keep gases in are relatively flexible materials. Best analog that we can have that's not like a gas cylinder would be like your car tires. The outer part of your car tire is a relatively rigid shell. So long as you maintain a certain threshold PSI, it holds a relatively rigid shape and a relatively constant volume. Now, if you get a hole in your tire and it goes all the way to flat, obviously the tire loses its shape. If you've got some kind of a leak in the tire and you're now reading at 12 PSI, it's gonna look a little deflated. But for the most part, it holds a relatively round, relatively constant volume. But you know as well as I do that the pressure inside of your tires does change seasonally. Right now, you wake up, it's cold. You end up putting a couple of extra PSI into the tires to make sure that they're inflated to the proper depth, that they're to the proper pressure. In the summer, it's hot. The pressure inside increases. You have to let a little bit of air out so that you don't overinflate the tires. There is a direct relationship there. The colder the temperature is, the lower the pressure is inside of your tires, the more air you have to add in to compensate. And so again, we see that this comes out in a division where factor 1 is divided and equal to our changes in conditions, factor 2. So those are our three primary gas laws. Each one of them does a specific job, tells us of a specific set of conditions where things can change or be modified, and holds together one of the factors as constant. But what if, for example, none of the factors were held constant? What if pressure, volume, and temperature were all changing all at the same time? Which is not as uncommon as you think. Well, one of the nice things is that those laws, because they contain the same factors and kind of the same orientations, we can combine them together. And the result that we get is something called the combined gas law. The combined gas law takes together Boyle's law, Charles' law, Gay-Lussac's law, puts them all together, jams the equations together, and gives us one unified equation. Now, you want to know the really cool thing about the combined gas law? It's actually the only equation that you need to memorize. And the reason I can say that is, let's just imagine for a second that we've got a situation where temperature is being held constant. Well, if temperature is held constant, T1 and T2 are the same. I can get rid of those terms and be left with just pressure times volume 1 equals pressure times volume 2. That's Boyle's law. And I could do similar kinds of things for the other parameters as well. If volume's constant, I'm left with pressure and temperature. That's Gay-Lussac's law. If pressure's held constant, I'm left with volume and temperature. That's Charles' law. All of those there are kind of contained within this. So if I recognize that one of my parameters is being held constant, I can make the necessary adjustment to the combined gas law to give me the right mathematical equation. So let's do some practice problems. We have a compressed gas held at 3.33 atmospheres of pressure and 35 degrees Celsius in a 5.5 liter vessel. If the vessel suddenly expands to 15.2 liters at 55 Celsius, what will the pressure inside the vessel be? So if we set up our combined gas law, we have P1 V1 over T1 is equal to P2 V2 over T2. Remember that our temperatures have to be converted to Kelvin. So I need to add 273 to each of these. 35 plus 273 gives me 308 Kelvin. $55 plus 273 gives me 328 Kelvin. So my initial pressure was 3.33 atmospheres. My initial volume was 5.5 liters. My initial temperature was 308 Kelvin. I don't know what the pressure is under the new conditions, but I know that the volume is now 15.2 liters. And we are at 328 Kelvin. We got to do a little bit of algebra here. We're trying to get P by itself. So I need to multiply each side by a fraction that has the 328 Kelvin on top and the 15.2 liters on the bottom. Do that to both sides. My liters cancel, my Kelvin cancel on the one side. So I've just got pressure. None of my numbers cancel on the left-hand side, but my unit of Kelvin and my unit of liters both cancel. I'm left with just atmospheres. Now we just need to do the math. 328 multiplied by 3.33 multiplied by 5.5 divided by 15.2 divided by 308. I get to 2 decimal places, 1.28 atmospheres as my pressure. You think to yourself, okay, does this number make sense? Well, I've got two competing factors here. We know that for pressure, an increase in temperature should increase the pressure. But we also know that an increase in volume should decrease the pressure. Which one changed by the bigger amount? Well, the temperature only changed by about 20 degrees, which compared to 308 degrees is really not that much. It's about 1/15 of the overall temperature. The volume nearly tripled, which means that the pressure would have gone down by nearly a third. So we're comparing a very small difference in temperature to a very large difference in volume. We would have expected the pressure to go down, which it did. All right. Any questions with regard to this example? Michael?
Can we choose which law we want to, or just the question give it to us?
Well, the question is going to dictate at least some of it to you. What I always would tell you to do is start with the combined gas law, and if there are things that don't seem to fit, you can remove them. But if you start at the combined gas law, you have a better chance of ending up going in the correct direction. All right, I'm going to let you all try this one. A certain vessel will rupture, explode, if the interior pressure exceeds 36 atmospheres of pressure. We have an air-reactive gas in a rigid 10-liter canister at a temperature of 25 Celsius and a pressure of 25.9 atmospheres. After being left out in the sun for the afternoon, the temperature inside the canister was estimated to be 75 Celsius. True or false? The canister ruptures. Okay, now I will warn you, there is a lot of information in this question that you do not need. Make sure that you're picking out the information specific to the gas itself as you're trying to solve this problem. So take about 5 minutes or so, try to work your way through this. We'll come back and talk about it. All right, so let's take a look at this problem. Now, again, one real key aspect of this, the fact that it is rigid, indicates that volume is constant, which means we can use the relationship between pressure and temperature, which would be Gay-Lussac's law. So there are multiple ways of solving this problem. We can look at pressure 1 over temperature 1 as equal to pressure 2 over temperature 2, which is kind of the conventional approach. And if we do that and we put in our values, remember we have to turn those temperatures into Kelvin. So 25 Celsius would be equal to 25 plus 273, which is 298 Kelvin. And 75 Celsius, well, that'd just be 50 more. And so if we did that and we took that initial temperature or the initial pressure, 25.9 atmospheres over 298 Kelvin is equal to our unknown pressure over 348 Kelvin. To solve, we would multiply each side by 348 Kelvin. That would get our kelvins to cancel on the left-hand side, the 348 kelvins to cancel on the right-hand side. We'd end up with a pressure .9 times 348 divided by 298, 30.2 atmospheres. And since that 30.2 atmospheres is less than the threshold, there's no explosion. So that would be one approach that we could take to solve this problem. The secondary approach would be, and I saw some of you, it looked like we're trying to do this, was what do I do with that 36? Well, I could use 36 in this place as well. It would look very, very similar. The only thing I wouldn't do is I couldn't use T2. I'd have to use the 36 atmospheres to figure out at what temperature would the rupture occur. And I could do that. The process is pretty similar. I got it. Now this one will be a little bit trickier because you've got a variable in the denominator, which means that basically you have to switch places. T2 comes over here. This entire fraction goes down here. So that we get T2 in the numerator. But that'd be 36 atmospheres multiplied by 298 Kelvin divided by 25.9 atmospheres. Atmospheres cancel. 36 times 298 divided by 25.9 would give us a T2 of 414 Kelvin, which would be minus 273, 141 degrees Celsius. We'd arrive at the same conclusion. The required temperature is greater than the actual temperature. So the answer to the question would be false. But this would be a secondary way to do it. So again, multiple approaches. Obviously, the first way is probably the most straightforward. But if you found yourself, unable to get around that 36 value, you could kind of figure your way through it that way. And so we're going to leave today. I'm going to give you a couple minutes to go over to the bookstore if you need to. We're going to leave today by kind of setting up the next concept for over the weekend and for Monday. And that is the idea of a phase diagram. So what a phase diagram allows us to do is it's basically a graph. You've got temperature on the one axis, pressure on the other, and it gives you a literal representation of what phase of matter to expect for a given substance based upon the temperature and pressure conditions. And so we'll get into more of the details of it, but this is what a phase diagram ultimately looks like. Again, it's a graph. But using the graph coordinates, we would be able to plot that for any pressure and temperature condition, this is what we would expect to see as far as the phase is concerned. And so we'll talk about that on Monday, and we'll apply it to, again, our first real class of hazardous materials, that is cryogenics, where we take a vapor source and condense it down into a liquid at low temperatures in order to help transport it more safely from one place to another. So that's what's coming up. That will end our chapter 2 discussion on Monday. Have a great weekend. I'll see you then.